Now, this is a little bit of a review, but something that I think we did before, but I'm not sure. Remember I asked you when I crashed Elaine's class, talking about division of fractions and how that's like the hardest thing conceptually that you'd be doing in an elementary level. It's usually 6th grade, so it wouldn't even be here. So, and I gave you this example, 2/3 divided by 1/6, and asked you how you would have done it. So if we flip this one, it would be this, right? Times 1/6, correct? So, let's not worry about the real answer yet. Let's look and see what this answer comes out. Karen's way, okay, taking the second one and flipping it. So, it would be 2 times 6 is 12, 3 times 1 is 3, and that can be reduced to what? 4. Okay? Or, if you learned other shortcuts, you could have done 3 into 3 once, 3 into 6 twice, 2 times 2 is 4, 1 times 1 is 1, 4 over 1 is 4, okay? So, this is telling me the answer is 4. To do it the other way, I'd get, let's do that little shortcut here. 3 into 3 once, 3 into 6 twice, right? 1 times 1 is what? 1/4. So my question is, what makes more sense? You're a kid, you're starting to do this. What have you learned all along about division? I'm saying it gets smaller. So you're in 6th grade now, 5th, 6th grade. But when we go back to when we first learned, 36 divided by 4 equals what? 9. 42 divided by 6 equals what? 100 divided by 10 equals what? They're getting smaller and smaller. Okay? But that's not how kids digest division at all. They don't really, even adults don't normally do that. What would kids normally think of?
It's the opposite of multiplication.
It's the opposite. So what is multiplication then?
Well, multiplication is repeated adding.
So this would be repeating,
so this
subtracting?
Is sort of like repeated, I mean, it's not, but it's sort
They
of
might
like
think
that.
that.
But if it's repeated subtract, why would this be the better answer than this?
We're doing this in class right now, and whenever I'm watching Lauren doing this, I'm thinking to myself, how do you articulate this properly? It's 2/3 divided into 1/6 chunks. But like, that doesn't really make it like.
For how many 1/6
Ah,
will fit?
You're getting
Yeah.
it, you're getting it, Karen. Okay, so
Yeah,
we're gonna
how
take
many
a,
1/6?
remember Karen's question, okay? How many will fit in, okay? So now, I gave you some pattern blocks around the room. Just take some out for now, and normally I would give you time to play. Just take a few out. I'm gonna ask you then, and here's a really important word. It's the very first word on the page. What is it? If, okay? It's a conditional. And that's one of the most important things in math, okay? If the yellow hexagon equals, now I'm going to say for the purposes of the next 5-10 minutes, this is going to equal 1, okay? If this equals 1, the red triangle equals what? 1/2. Not 2, 1/2, okay? So that will equal 1/2. Prove it visually, show it to the person next to you, build it somehow, okay? And then the next question is, what does the blue rhombus equal? Or parallelogram? Again, build it. That's not always easy for especially adults to see. The adults sometimes have a harder time building this than the kids do. You want to put those 3 blue ones on there so it fits. Can everybody see physically how it's 1/3?
Yep.
Okay. And then what about the little green triangle? How many?
6.
Good. And again, build it, prove it. So forget about what's on the board for now. Let's just focus in on these rods intensely, or these pattern blocks, for a few minutes. Okay. So now, the next thing, there's a little equation there for
A
you.
couple more.
It has 2 triangles put together, the 2 green ones, and it has a line plus a line equals something. What do you think that's a visual for? Evan?
1/6 plus 1/6.
1/6 plus 1/6. It does equal 2/6, obviously, but what else does it equal?
1/3.
Chelsea just held up 1/3. Half plus 1/2 equals 1/3, right? Then we have the next one down there. We have a parallelogram or a rhombus, the blue one, plus a triangle. Okay? And now this is when you have what's that? Again, Karen and Aaron are in this deeply now, okay? I know that Chelsea's in it somewhat now, unlike denominators, correct?
Yes, just started that today?
Just started it today. So we have this little guy, which is 1/6, and we add to it 1/3. What is our answer?
1/2.
1/2. Okay. Now we could have divided this into those two things, and that could have been 2/6, correct? And this would have been 3/6, which still equals 1/2. So again, we're showing the kids what and how, not just the algorithm. Okay, the algorithm are those things we did on that other page. Take the second one, flip it, do that little thing that I did in Catholic school, or take 3 and 6 and reduce them to 1 and 2 on either side. I did half of that stuff not knowing why. It's just the algorithm, they told me to do it. I didn't know why. So finally, get to that last one and work it out with somebody next to you or across the table.
All right, so here was the original
Picture.
picture, which is 1/3, and this one can be 1/2. But if I rearrange them into this shape and compare it to my original whole, I can see that it's 5/6, just like this would be 5/6.
Okay, so everybody look at what Karen did. She did it like this. Did somebody do it a different way? I thought you started to figure out a different way.
Well, I just said that I see it looks like this, and I can fit 1/6 in.
Mm-hmm.
So I know that this must be 5/6 because I know that one hexagon is worth 6 out of 6 green triangles.
Very good. And if we wanted to make them all the same denominator, what's another way we could have done them with the blocks? Leave yours just the way it is, Dinah, and take out 5 triangles and lay the 5 triangles right on. So the blue became what? 2 greens, which is 2/6,
3/6.
and the 1/2 became
3/6.
3/6. What's 2/6 plus 3/6?
5/6.
5/6. What's 2 bananas plus 3 bananas? 5 bananas, right? So there's so many different ways that kids can do it, and again, they're actually seeing what and why things are happening, just not memorizing the algorithm. And then you go back to this same example, and if you think about the language, it's not just the experience, it's the language. You started to say it, Karen. What were you talking about? Changing it around.
How you describe what division is doing?
Mm-hmm.
How many 1/6 will fit in 2/3?
You're so close to the word I want you to say.
Go into?
Yes, there you go, okay?
Goes into, as Elaine goes into.
Exactly. Well, Elaine got Gazinta from me,
Yes.
I got Gazinta from
Gazintas,
Lola May.
yeah.
So go back to these original things. When kids are learning this, we're telling them something that's almost unnatural. They don't think about 36 divided by 4, because divided by 4 is a hard concept to do. They're thinking, what, 4 Gazinta 36, how many times?
9,
6 Gazinta 42, how many times?
7,
10 Gazinta 100, how many times?
10,
6 Gazinta 12, how many times?
2.
2. So now, after you had just a little bit of experience with these blocks, put this into Gazinta language. 1/6 Gazinta 2/3, how many times? Put 2/3 in front of you, 2 blue ones. And how many 1/6 fit onto that? 4. Now the answer makes sense. When we say multiplication, what we're really saying is of. So let's visit this a different way. 2/3 of 6. If we broke 6 into 3 equal groups, how many would be in each of the groups? 2. 2 of those groups would have how many pieces altogether?
4.
4. So then the answer makes sense. Models, fraction models, there's basically 3 kinds. Okay, there's a linear model, there's an area model, and these two are related because they're parts of a whole. A whole. And then there's a set model, which are parts of a set. So, a linear model is something as simple as a ruler. Okay, in a lot of ways, what we're going to look at next, these are also linear models. Okay, so if this was 1, the yellow would be what? 1/2, and you could prove it. Okay? It's the same, this was an area model, right? But this is kind of a linear and an area model. I think these are really powerful manipulators. That's why we're going to spend a little more time with these in the next few minutes. And then, of course, there's a set. Those are things like a Hershey bar, or a pizza pie, or socks in a drawer. You know, a Hershey bar or pizza pie would be more of an area model. So if the orange is 1, which is what we're going to spend most of the day in, what would the yellow be?
1/2.
1/2, okay? If the orange was 4, what would the yellow be?
2.
2, okay? If the blue was 1, what color would be 1/3? And again, you might need other rods to
Light green.
light
Light
green,
green.
okay? This could be 1, and if this was 1, then this would be 1/10, right? So it's all relative. As a matter of fact, when they go to use those bigger sets of the powers of 10 blocks, this is a 1, this is a 10, then there's the 100 flat, and then there's the big one. So now, it's 2 rods, the train is as long as brown, the difference between the 2 rods is red. X plus Y equals what? 8, right? And the difference between X and Y is what? 2. We don't know if it was Y minus X or X minus Y, so we use that calculation. The difference between the 2 is 2. So what those 2 numbers would have to be is 5 and 3. Okay? Now again, most elementary school kids aren't going to go up to this kind of algebraic writing, but they are asked to be doing the reasoning.
They don't have the manipulator.
Okay.
You had to start.
I've hidden all.
This could be the longest
your
one.
rods, so
It
I
can't be
don't
bigger
know.
than that. And if they're all different, you're only left with those
So the
4.
next one is 3 rods. You have to
So
go.
longest.
Got it.
You can't go any bigger, so.
No, that is long.
These clues you'll be able to figure out.
There's your rod up, boy.
It's
It's like green theory.
And the next one is, okay, so you don't want to have them connected because they're separate entities here. There we go. Okay, but what do you think the next one in my pattern will be?
Y.
Purple.
Oh no, P.
P.
Nope, good guess. And I'm totally giving you no reason for doing
R.
this. It's going to be 2 R's. So do this, 2 R's. Okay. Now what do you think the next one's going to be?
Oh.
Mhm.
Oh, I remember you doing this the last time.
2 light greens.
That's a good guess, but the 2 light greens doesn't come until quite a bit later. It's going to be over here somewhere.
Wait, if there's
Actually, I'm going to lay mine down because they're going to tip, okay?
4.
But
Oh.
And
Two,
this is
3.
3.
What do you have here?
this is 4. Yeah, so what's going to go here?
5.
So
We have to make 5.
5.
All right,
Yellow?
yep, yellow. Don't agonize over too much, it's a yellow. Okay? Now what comes next?
To 6.
It's going to be a
3 reds.
3 reds is a really good guess.
2 light greens.
Ooh, that one's already here. And as a matter of fact, your 3 reds are going to go right before the light greens.
What? 1, 2, 3, 4, 5. 6 whites?
Purple. No,
A purple and a white. 8. How much is purple?
2. Oh no, not 2.
A purple and a red?
Karen, how did you do this?
I didn't do that one.
Who did this one? Who did the
Karen
2?
did that.
I thought Karen did it
You
too.
told us.
You told us that.
Oh, I did?
A purple and a white? A purple and a red?
Wait. 1, 2,
6 whites.
4.
Okay, I'm going to tell you.
Why is
Nope,
that?
good guess though. It's going to be
So wait,
something to
it
do with
has to be
6.
6?
Yeah,
A purple and a red.
that's a good guess too.
How about a green and a red?
Yes, a green and a red. Why, Karen?
Because 2 times 3 is 6.
You're getting there.
It's multiplication.
Yeah, okay. Now, this one I'm not going to hold you to suspense is the black.
A green and a red.
Okay.
because these are all your primes.
You got it, Karen.
Oh, what?
They're prime numbers.
Okay, so Karen figured something out. These are prime numbers, okay? You are never going to use a white again, and you're never going to use any color that isn't here other than white. So that means you could only use red, green, yellow, and
Black.
black, until we hit another prime, and then we run into a problem.
Yeah.
So what is the next number? In number sense, count with me.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
2 times
So 2
5.
times 5.
Very
So
good.
red and
Red and yellow.
yellow.
Red and yellow, yep. Okay, now we do run into a problem because 11 is prime, so I'm just going to put a little placeholder here. What comes next?
12.
How are we going to build 12? You can only use these
3
colors.
and 2 reds. I'm sorry,
Three.
green, yeah, green.
Let's check that out. 3 times 2 is,
6.
times 2 is 12, okay? And then we get 13, which is another prime. I let the kids struggle with this a little bit more. They eventually get it, especially in 5th grade, because they've been studying it. What's going to be the next one?
13. I'm sorry, that was 13.
That was 13, yeah?
14.
2 times 7.
2 times black.
Mhm.
Red.
And then we're going to do 2 more, because 16 is a nice number to end at for this.
14, 15. So
3 times 5.
light green and
5
yellow.
times 3.
Very good. That's 15. And then what would the last one be?
3, before those.
Wait, what's this one? 1, 2, 3, 4, 6.
6, 7,
So
8.
8
4
times
4 reds.
2.
4 reds. Okay. And we're going to stop here. We can go on. And usually I have the kids go up to at least 32 over a couple of days, especially in 5th grade.
And you just have placeholders for
Yeah,
these
they
off
pick what
Okay.
they want. This is often what they pick because they're very
Okay.
handy. Sometimes they just use those little squares. Because when you get to 22, for instance, they end up building this.
Okay.
2 on top of an 11, and they just write the number in here. So
Okay.
this is 11, this is 13. 26 would be a 2 on top of the 13. But getting up to 16 is enough to prove what I was saying to you, what I want you to see from it. Often the kids then want to go up to like 100. You know, I usually get the kids to go all the way to 32. Because then if you did build a number like this, what would this number be in our pattern? 3 times 3 times 2.
Thanks, Michael.
That's 18. Okay, thank you. That would be over here, right? 17 would be another little blank one over here. But if I took the 18 and I took the 6, that's not a good color for that. I can see what they have in common. What do they have in common?
Green.
Green
2
and
and a 6.
2 and a 6.
I'm sorry, 2 and a 3. So they have
Which is 6. So 6 is the greatest common factor of both of them.
Wow. That's really cool.
And then as they start to get even bigger and bigger numbers, and when they take the numbers apart, we call them towers, you know, the kids like to try to stand them up. They could really start to see what the least common multiple is, the greatest common factor. Because how do you remember to get the least common multiple? What's the formula for it?
Multiply the number.
least common.
Break them
Oh,
down.
multiple on-
I should know this from MTELs.
You take away the greatest common factor, and you multiply it by whatever's left.
I never knew that.
So, and this one is pretty easy because it's 6 and 18, so the least common multiple is 18, because it happens to go into it,
I
right?
think I learned that.
So if we pick, let's pick a higher number just to play with it. So suppose we picked,
Yeah.
okay,
Obviously didn't stick.
what number is that? You have to do a little mathematics here, I'm pushing you way up.
So that was already our 18
One
times,
times 3.
Yeah,
Seven.
we'll leave it the 18.
18 times 7.
Oh no, because that's gonna be in it.
Sixty-three.
We don't want
Times
something to be in it.
126.
Okay, what's 3 times 3?
9.
Times 3
27.
times 2?
54.
54. And now this one is going to be 5 times, well, we could 5 times 9. We could take a
No,
little.
it's not a 5 though. It's
Oh, it's a 7. I want it to be a
That's why I
5.
was
That's
like,
why
I
I
was- I thought it
Yeah,
was
because I was like, it's 126.
Okay, so 5 times 9 is
45
times 2 is
90.
90. So 54 and 90. We can see pretty clearly what their greatest common factor is, right? It's 2
Yeah.
and 1. 2 3s and 1 2. So that's going to be 3 times 3 is 9, times 2 is 18. So 18 goes into both of them. But if I remove that from one of them and multiply with what's left over, that's going to be their least common multiple.
Okay, that's cool.
Wait, say that again? If you remove?
The greatest common.
The greatest common factor, you only need it once. So I'm going to get rid of one of them. And whatever's left here,
Oh.
that's going to be the number that both 54 and, what number was this one again? 90 go into. So it'll be 90 times 3, which would be 270. So 270 is the first number that both of them go into. And that makes sense to me. But this came out like at end of the 80s. It was this thing, 293 plus 293 plus 293 plus 293 plus 293 over 5 equals x. What's x? Quickly. Quickly.
293.
All right, okay. But what they found was,
Cross out the 5s and then you have x equals 2.
It's 5
if it was
times
orange was orange was orange was orange was orange divided by 5, it's going to be orange. If it was 2 plus 2 plus 2 plus 2 plus 2, right? Divided by 5, it's going to be 2, because 5 of anything divided by 5 is going to be the thing. But what they found was, this was back in the late 80s, the kids in high school, American high schools, the kids that were in the AP classes,
So adding together?
they took longer to do it than the kids in the next 2 sections or 3 sections below it. Because they were so nervous about not adding it, making sure it fit, that, you know, you take, say it was AP and then there's like 11.1, 11.2, 11.3, 11.4, all the way down to like 11.5 or whatever. The 11.1s and 2s, they'd be like, 293. And it was a much more relaxed approach. It wasn't like trying to figure that out over in the corner. And now think of how much has changed since then, even since the late 80s, with everybody has usually a device in their pocket that has a calculator on it. So those places where you're going to be spending time adding up long things, it's not so economical to do anymore. You want to be teaching the reasons why things work so people are not mired in the minutia. And I'll use that 6 plus 7. And then another one is 7 plus 6. No matter how well we think we're teaching this, kids will still think these are 2 different concepts. Then they're going to think that this is a different concept, and that this is a different concept. So by limiting to those rows of symbols, we're actually quadrupling their work. The concept is these 3 numbers go together somehow. And as a matter of fact, a lot of kids were octupling their work because some of them won't even realize that this is the same as this, is the same as this, is the same as this. So then you have this, and then you'd have this, and then you'd have this.
I'm just figuring all of this out now.
So we've made this little idea, 6, 7, and 13, all go together, 8 times as hard for certain learners. And that percentage goes down as they develop. But when they first get it, you know, for half your class is going to think this is different.
So finish off the diamond again, I forget how the bottom goes with the multiplication.
Well, then after first, second
you
grade,
do all this, then
okay,
you guys
and then I just switch the direction of the diamond to do the multiplication. So if we have 7 here and 6 here, what's 6 times 7 is 42.
And you just put them together.
Right. So then that becomes what you
Yeah.
memorize. And then years later, now if I didn't hand this handout to you, I will. So end of 3rd grade, beginning of 4th grade. 4th grade is a great time to teach this. You add the north, east, south, and west component. And then if you say, if I put 9 in the south,
No,
or
so
the
north,
west,
I was
sorry,
gonna say, wait a minute.
west, and 5 here, what goes in the north?
14.
14, because it adds up to the north, and what goes into the south? 45. And here again, you get so much easily understood algebra, because if you always have the north, east, west, and south, they will start to, and let's put our things here, 42 and 13. Okay? West plus east always equals what?
North.
East plus west always equals north. It's the same thing that we did on that other page. North minus east equals west.
Yeah.
North minus west equals east. And then, again, talk about something that's just arbitrary. We do multiplication. We would do this, but kids would do this. Okay? Some kids could even do this, or even this now. right? So like even the multiplication symbol is arbitrary. So let's use the more traditional one. That's going to equal south. East times west will also equal south. And then talk about also arbitrary. This could be divided by, this could be divided by, right? So south divided by west equals east, and south divided by east equals west. Once they get that concept that all those 8 things are the same, all you really need is the box with the numbers. So it doesn't matter what numbers I put in here. Then you could add like the zero tricks. So like say this is 700 and this is going to be 760. So what would go in the east?
66.
And then what would go in the south?
42,000.
42,000. 7 times 6 is 42, and then 3 zeros, right? 42,000. You could put just the south in it. You know, you could put down. Well, zeros and ones are always funky to put in it, and then halves, fractions are even funky to put in.